power grids. Actually, it's a sensor for the detection of transmission towers. And we may wonder what this is useful for. So I will start by giving a bit of motivation for this work. You all know the skyline of New York, of course, and most of you also know that in 2003, suddenly the skyline looked like this. So there was a very big power failure that was widely reported in the news. And now let's look a little bit into the reasons for that. What happened in 2003 was the following thing. In the afternoon, there was a tree in Ohio that brushed a high voltage line. And this led to a succession of events that were not great for the power grid. So essentially, there was an alarm system that failed at the power company. And the operators tried to understand the reasons why they had a failure while having no alarm. And this led, in the meantime, to overload on some other lines because they were not able to react in time. These overloaded lines eventually cut out because they had too much load, they overheated, and this went to a cascade of failure that in the end led to 15 million people without power for up to 2 days. So what we know from this case and from similar cases that happen regularly but not at this scale is that a quite small event can lead to a relatively disrupting event in the end. So what we are trying to do here is to prevent the cause of these kind of outages. So actually we would like to be able to see with our sensor what happens to the power grid, and very specifically we have now focused on power masts or transmission towers. So we would like to see events like these ones automatically and to characterize them, to tell an operator or to tell a power company what actually happened and where. Nowadays this is done by sending somebody to the site, that somebody drives around with a car and tries to locate the fault, and he reports back, and then a team comes with material. This all takes quite a lot of time and leads to expensive cost when 50 million of people are affected. Our goal, and we are not there yet, you will see it, but we did a first step, is to have a sensor mounted on a drone, for instance. So it's essentially a camera that finds the error automatically and also reports on its nature. So what happens to which kind of equipment. So let's now go to the method. Of course, we don't have time for all the details, but essentially the method that we use to localize these towers is a learning-based method, which is illustrated here. So there is a first phase, the training phase, where a characteristic object representation of transmission towers is learned from a training set. And then there is the actual detection phase, where image features extracted from the video that you are looking at or from individual images are compared to this model in order to detect matching entries. So it's a very classic approach, but applied to a new scenario. Now let's look a little bit in details into each of these two phases. The training phase, first of all, you have, and that's always very crucial, you have to extract features that are meaningful. This is relatively easy for human faces, for instance, and it's much more difficult for transmission towers. First of all, because they are very diverse, so a telephone pole doesn't look like a high voltage tower, and also because there is not much that characterizes them. I mean, you almost don't see a color, and it can be diverse, the shape can change, etc. So we have a bit focused on this grid shape that you have in transmission towers, and therefore we are using a line segment detector. The name LSD, of course, here means line segment detector, which extracts straight lines from an image. It's a very powerful detector. It's not from us. It's something from the literature, but it gets you all the lines. And then you have from these lines to build a model, because of course you have many, many lines in an image, as we can see here, that do not correspond to a tower. What we use as a model is called shape tokens, and this is illustrated on the bottom there. It's basically a geometrical model that captures, it takes pairs of lines and it captures their geometric relationship in terms of angle, in terms of length, and in terms of distance. This is then clustered, so we do this on our training set. We extract all the shape tokens that we can, and we cluster them using, in our case, a K-Medoids clustering algorithm that's essentially similar to K-means, but extended to other distance metrics. The distance that we use is called shape distance. The details are in the paper, but essentially it's a weighted average of the different characteristics that we have in a shape token. And this is not enough. These clusters, they allow us essentially to know what a tower looks like, but then we also want to know where how these shape tokens are distributed on the tower. And for this, we learn a spatial distribution associated to this, to the actual clusters. With this, we go into the detection phase. In the detection phase, first of all, there is a feature extraction phase exactly similar to the previous one, but now for the image that we work on. And then we have a matching and voting scheme based on the generalized half transform. So first, each shape token of the current image is compared with the code words, so with the ones that we have in our reference set. And if the distance between the two is inferior to some threshold, then we detect a match. Once we have a match, and I think that, yeah, actually it's somehow blocked, so I briefly have to restart the presentation here. Yeah, the animation doesn't work for some reason. Anyway, once we have a match, a vote is cast in a 2D space, a half space, and if the density of votes of the actual image at some locations exceed another threshold, then we have an object detection. And so this gives us the location of the center of the objects, but then we need we want to have an actual bounding box around the object. So what we do first is a bit of regularization in order to avoid local minima that are not meaningful. And then we localize maxima according to a method that is again taken from the literature described in our paper. And finally, we indicate the towers by, for the moment, a bounding box with a fixed ratio. That's not great because in reality you have things like occlusions that happen and you have different types of towers, but it's a good start. So now I have no idea why PowerPoint doesn't work the way I wanted, but let's go on to the validation. We did the validation the following way. First, we had to build a test set. There is no standard test set right now existing, to our knowledge, in the world for this particular application. So we took images from the internet, only 100 for the moment. We will do it with more in the future. We already started that, as we will see in the conclusions. They include 212 towers in total. Our training set has been built from 15 randomly selected of these images, and these contain 31 towers that are used for training. And then we did a qualitative assessment and a quantitative assessment, which I will briefly show now. The qualitative assessment is really essentially running some images through the algorithm and seeing what we get out of them. Here I'm showing examples that work well. In the appendix I have examples that don't work so well, but I only show them if there are questions about this. Not because they don't work well, but just because of time. So what we see here is that in general, even in the presence of background clutter, and that is really an advantage here, we are able to localize the masts and also multiple masts to some extent, although here we already see the limitations. I mean, one mast in the background is missed, and one is confused with the street lamp, of course, but qualitatively this seems to perform, let's say. Then we did a quantitative validation. It's a precision recall curve. So I don't go too much into the details of what this means, but essentially this gives you the the true positives, so the objects that have really been detected, and the negatives, so the objects that have been missed. And why a curve? Because you always want to do this over a set of variable parameters. So in this case, what we have varied is the threshold on the voting score, which indicates the detection confidence. And by doing this, you are able to reach different trade-offs between detecting all the objects, but also many things that are not real power towers, and on the other hand, missing too many objects. So these are trade-offs that you want to vary depending on your application. This trade-off is shown here. Of course, the more area you have under the curve, the happier you are. And what we can see here, we have looked at two cases, one where we ask for an overlap between the ground truth boxes of 50% and the detected boxes, and in the other one only 30%, so the other one has to have a less precise detection, the thick curve. But what we can see is that the performance so far is okay, but not great. Of course, what's missing here now is the comparison with competing methods, and the reason for that is that the first real serious paper on this has appeared a month ago, so we were not able to do this, but we are doing it currently. But this performance certainly can be improved. So in conclusion, the first thing is what I showed in the initial slides. I mean, in our very particular area of power grid management, this is a very important work. So we need and we want in the future to be able to perform such tasks automatically, because sending troops there and experts is simply too time intensive and too expensive. We also see that we have detection with our method, so it works. It works even in more complex scenarios with multiple towers and with a cluttered background, but there is still room for improvement, and that's what I'm talking about here. We would like in the future, first of all, to characterize ourselves with respect to the competition. That's very important. We want to have our detection scale invariant, because right now we need to go through a pyramid of possible scales, so possible sizes of the tower in the image, and this of course is a limitation because it increases your memory requirements. You need to build models for all these scales. We want to use more distinctive object features, but that's not easy. I mean, this LSD that I was talking about is not so bad. It's hard to find something better than just intersecting lines on a tower. And finally, the voting scores is certainly something, right now it's very naive. It's basically the density in your half space, and we can probably do better there. So this is, in a nutshell, our method, and now the floor is open for questions.